this video, we're going to be talking about triangles and trigonometry. We're going to look at similar triangles and then two different types of special triangles. So if you remember, two triangles are said to be similar if their corresponding angles are the same measure. So we have this large triangle here and this smaller triangle right here, and we want to look at their angles, alpha and beta. So we're going to use SOHCAHTOA in order to look at angle alpha and angle beta. So if I look at the sine of angle alpha for our large triangle, we have alpha opposite, so that's 16, over my hypotenuse, which is 20. And that's going to reduce down to 4/5. Now if I look at the sine of alpha of my little triangle, I have opposite, which is 4, over my hypotenuse, which is 5. So I end up getting the same answer, 4/5, for both the large triangle and the small triangle. So as we can see, the trigonometric function values depend only on the measures of the angle, not the size of the triangle. We can even prove this even further by looking at another example. Let's look at the tangent of angle beta of the larger triangle. So with the larger triangle, I have beta down here, and I need opposite, which is 12, over adjacent, which is 16. That's going to simplify down to 3/4. Now if I look at the tangent of beta for my smaller triangle, I have opposite, which is 3, and adjacent, which is 4. So again, I get the same answer. I get 3/4 no matter if I'm looking at the big triangle or the small triangle. And we can use any of these trigonometric values, sine, cosine, tangent. It doesn't matter. The angles are still going to equal the same thing. All right, so now we're going to talk about the first type of special triangle, an isosceles right triangle. If you remember, an isosceles right triangle has two equal angles. So this angle here equals this angle here, and two sides of equal length, which means this side equals this side. So if you remember, the interior angles of a triangle must sum to 180 degrees. And we have this right angle here. So I have 180 degrees minus that right angle, which is 90 degrees, and that leaves me with 90 degrees. But I have to split this 90 degrees between these two angles that must be equal. So I need to divide 90 degrees by 2, and that leaves me with 45 degrees. So that means each one of these angles has to be 45 degrees. Now, as we saw in the previous example, trig values are independent of the sizes of the triangle. So we can just choose whatever we want our legs of our triangle to be. And in this case, I want to choose that each leg equals 1, and they have to be the same because it's isosceles triangle. Then we can find the length of our hypotenuse. Let's go ahead and just call that C. So using the Pythagorean theorem, I have opposite squared plus adjacent squared needs to equal my hypotenuse squared. So I get 1 plus 1 equals C squared. 1 plus 1 is 2 equals C squared. Taking the square root of both sides, I get C is equal to the square root of 2. So now that I have all of these values for my triangle, we can now determine the trigonometric values for the angle of 45 degrees. So I'm trying to find the sine, cosine, tangent, cosecant, secant, and cotangent, all of this 45 degrees, using the values that we just found in our previous triangle. So we're going to use SOHCAHTOA. So I have the sine of 45 degrees. You can pick whichever 45 degrees you want to work with. In this case, I'm just going to pick this one. So I have the sine of 45 degrees equals opposite, which is 1, over my hypotenuse, which is 2. But we don't want to leave a radical in the denominator, so I need to multiply both top and bottom by root 2. And that's going to get me root 2 over 2. Cosine is adjacent over hypotenuse, so we have 1 over root 2 again. Simplifying again, this is going to give me root 2 over 2. Tangent, opposite over adjacent, so we have opposite is 1 over adjacent, which is 1. 1 over 1 is just 1. So then I have cosecant of 45 degrees. Well, if you remember, cosecant is the reciprocal of sine. So we're actually looking for 1 over the sine of 45 degrees. And since we've already found the sine of 45 degrees right here, I can just simply say 1 over the sine of 45 degrees, which was root 2 over 2, and that's going to simplify to square root 2. Since we know that cosine is adjacent over hypotenuse, since secant is the reciprocal of cosine, we know that secant is going to be hypotenuse over adjacent. I know my hypotenuse is root 2 and my adjacent is 1. So that's also going to leave me with root 2. So either way that you choose to do it is just fine. You're going to get the same answer. Same with cotangent. If I know that tangent is opposite over adjacent, cotangent, its reciprocal, is now going to be adjacent over opposite, which is 1 over 1, which is just 1. So these values are going to be very important throughout this course and will be used quite frequently. So make sure that you really understand how we were able to obtain all of these values. All right, the next special triangle that we're going to look at comes from an equilateral triangle. So if you remember, an equilateral triangle has 3 equal angles and 3 equal sides. So as you can see, all of my angles are 60 degrees, all of my sides are 2. It is an equilateral triangle. So in order to make a right triangle, we need to bisect this angle. So when we bisect that angle, it's going to cut that angle in half. And when I bisect that angle to the opposite side, this side is now perpendicular to that line. So now basically I just want to look at half of this equilateral triangle. So I'm just going to pick this half. So as you can see, this angle is still going to be 60 degrees. So here's my 60 degrees. I have my right angle here and my right angle here. So here is my hypotenuse, which is 2. So my hypotenuse on this one is still 2 because that did not change. As I said, when we do the perpendicular bisector of this line, it's going to cut this line in half. So if that whole distance was originally 2 and we cut it in half, it's now going to be 1. But now we need to find the height of this triangle. In order to find the height of this triangle, we can use the Pythagorean theorem as we did in the previous triangle. So we have the leg squared plus our other leg squared, which is what we don't know. So let's just call that b. B squared equals our hypotenuse squared. So that gives me 1 plus b squared equals 4. And subtract the 1 from both sides. I get b squared equals 3. Take the square root of both sides and I get b equals the square root of 3. So now that we have all of our values for our right triangle, we can find again all of the trigonometric values for these two angles, 30 degrees and 60 degrees. So I'm always going to start off using SOHCAHTOA. All right, so we're looking for the sine of 30 degrees. So here's my 30-degree angle. Sine is opposite over hypotenuse. So opposite is 1. Hypotenuse is 2. So the sine of 30 degrees is 1/2. Cosine of 30 degrees, we're looking for adjacent, which in this case is square root 3, over my hypotenuse, which is 2. Tangent is opposite, 1, over adjacent, which is root 3. Again, we don't want to leave a radical in the denominator, so I need to multiply both top and bottom by root 3, and that leaves me with root 3 over 3. Now we're going to do the sine, cosine, and tangent of 60 degrees. So down here's our 60-degree angle. Sine is opposite. So now our opposite is root 3, and our hypotenuse is still 2. Cosine of 60 degrees is now adjacent, which is 1, over our hypotenuse, which is 2. And finally, tangent is opposite over adjacent. So 60 degrees opposite is root 3 over adjacent, which is 1. So that's just root 3. All of these values are very important, and we're going to be using them throughout the course very, very often. So really make sure that you understand where these values are coming from, and you'll really be able to see how important these values are once we derive the unit circle later on in the course.